in this video we're going to learn a new subchapter which is on data structures or data organization, which is more into coders. Previous subtopic you look into numbering, you look also on conversions numbers. So now we look more deeper because you already play around with 1010 coded, you play around with binary, etc. So now going to look into more adventures and advanced in coded. So first of all, let's we understand and remember on the term of bit, nibbles, bytes, and words. So the data organizations also a value may tag an arbitrary numbers of bits, so over here, and the common collections are single bits. So smallest unit, so you need to know smallest unit we call as bit. So you have 1 bit, 2 bit, 3 bits, and etc. And groups of 4 bits, you will call it or you will get it as nibbles. So if let's say you have 4 bits, you will get a nibble. And how about next, which is it is a 8 bits. If 8 bits, you will get byte, 1 byte, 1 nibbles, 1 byte, and then this one is 8 bits, and another one is 16 bits, which is similar bits over here, and you will get a words. So please try to remember this. The singles or the smallest numbers or unit it called as bit, and then 4 combinations of bit you get nibbles, and 8 bits you call as bytes, and also 16 bits you get 1 words. The bit is in a byte are normally numbering from 0 to 7, similar like previous chapter. You know that it will started from 0, and you have 8 over here on the byte, so total is 8 bits, which is you start from 0, 1, 2 until 7. All together you get 8 bits. So next, okay, this is the examples on how the bytes look like. So how you're going to know this one, you already learned also, and in the LSB, which is least significant bits, and bits 0 is the lower or low or the bits which is on your rightmost. So from your right it called LSB, and from your left it called M, which is most significant bits, which is MSB. This one is you already look into previous video. If you still don't memorize it and you did not yet see, please take a look previous video that I already shared. And please take note that 1 byte also contain exactly 2 nibbles, because 1 nibbles we contain with 8 bits. So if we want to have another nibbles over here, we have all together 8 bits, sorry, so you will get 1 byte. So this is the example, which one is on your left is MSB, for your right is LSB. And now it is let's take a look on, because you already understand on bits, which is the smallest unit. Now first we going to look into nibbles. So in here you know that its content as many as 4 bits, and how it's going to look like is like this. And where you normally use the nibbles is on binary coded decimal or BCD, and on the hexadecimal numbers. This is the examples of the binary coded decimals and also in the hexadecimal numbers. So quite simple, you just know how and where you apply nibbles basically in the coded and also in numbering system. And you know that BCD use the nibbles and hexadecimal numbers too. And let's take a look on bytes, which is you need to have 8 bits altogether, and the total value is to the power of 8, which is you get 256. So where you apply this byte, which is on the numeric values and also sign numbers. So this is also the range for all bots major use in byte. Now let's take a look on words. Word, you know it is 16 bits, which is occupy 2 bytes, and bits 0 to 15, as I already mentioned, that everything will be started from 0. So the value is to the power of 16, you get 65,536. And over here it is the example how it's look like on the byte. If you have a byte, you will get 2 bytes equal of 1 words, and over here you have 4 nibbles, you get 1 words. So this is happening and the usage also in the computing, except on the header. You need to look into header, how many bit, how many byte, the header for TCP, the header for any other protocol. You need to know on bits and bytes, and how many bits, how many bytes for each header that occupy. Later on I think you will learn on that basically in a networking subject. So the major uses for words is on the signed integer numbers and also unsigned integers and also Unicode characters. So what basically codes are, and what its implementation, and why we need code. So code is representations of information generated by following certain rules. And why it's important is because code is unique. So it is unique, and then so first is code is unique, and then code are easy to process, easy to represent, and the last one is code enable communication, let's say on the different field of original spoken, writing and language is difficult and impossible. So the example is Morse code. Due to this, code can simplify the process, just as manipulations and arithmetic or algorithm of the informations in the digital system. So what we're going to learn in this video, in these subtopics, is 4 codes, which is first is BCD, and then second is gray code, third is ASCII code, and last one is parity code or bits. I think there is another one. We will learn the parity codes or bit first, and then lastly is on the ASCII code. So first we're going to learn on binary coded decimal BCD. If we look here, we can say that BCD is the way to express each of decimal bits with binary. So any numbers of base 10 or decimals, we can show it in a binary. Basically this very easy because you already learned on decimal base 10 and binary base 2, and how you're going to convert between both parties. And there are only 10 code groups in BCD system, one for every digit, which is from 0000 to 1010. Why? Because you only need 10, which is from 0 to 9, similar to the decimal digits that available. And that's why there is other coded in binary which is not cannot be used, which is invalid code, like this one, which is represent as 10 decimals, and then this is 11, this is 12, 13, 14, and lastly 15. So this is the invalid code. So this table is occupied and shows all the binary coded which is represent for the decimals itself. I think this one is just a conversions between decimals to binary, so it's quite easy. So this is on binary coded decimals, or it called as BCD. How are you going to convert it? This one you need to know that it's not directly convert using the binary to decimals. Last time you can see that you can directly convert 0 to binary, you can convert 1 to binary, which is you just occupy the binary code. But now it's binary code decimals, which is you need 4 bits in every single one digit number. So over here in your decimals you have 1 digit number, but in BCD you need to have 4 bits. 1 digit you need 4 bits. So over here, if let's say you have 3, 2, 4, 5, how many bits you're going to have? Which is, this is 4 bits, this is 4 bits, similar to this one. So all together you will get 16 bits. So each of them you need 4 bits, 4 bits, and 4 bit 3, 2, 4, 5. So from here you will convert it 5. Normally you will get as 0101. Why? Because 1, you starting from here, it is to the power of 0, to the power of 1, to the power of 2, and to the power of 3. So please remember this, because you convert it using binary, which is base 2, and this is just a normal binary coded, so it's easy for you to remember exactly how you're going to get. So over here, if you can see that you have 3, 2, 4, 5, So 5 you already convert it, you get over here 0 1 0 1, and then you have over here is 4, so that's why you get 4 over here, and then another one is 2, this is 2, and this is 3. So if you don't understand, please try to do it manually, like this one. If you have 0 0 1 1, how you get it is to the power of 0 to the power of 1, so you get 2 plus 1 equal to 3. So that's why you get like this. So next, which is example 2, you convert 7848 to BCD coded. Similar also, you will convert 8 to binary. You will get 1000. This one is represented as 8, and this is 4 8 7. Where is your BCD? BCD is the long digits here, which is occupy 16 bits. So 32, 3245 for decimals number, you will get the BCD as 0 1 1 0 0 1 0 0 1 1 1 and 1010. It's really ugly. Okay, next, after you already learned the first coded, which is under BCD, binary coded decimals, you're going to move to new coded system, which is called as gray coded. So what is the gray code is to design to prevent false output from electromechanical switches, and basically it's widely used for facilities error corrections in digital communications and etc. So you can just read it, go through it on your modules. It's just similar, but I want to discuss and show how it's basically going to look like. Over here, you need to know what is the method and approaches. From the binary, you will get the gray code. You cannot directly convert the decimal number to gray code. You need binary in between before you can convert decimal to gray code. You need a binary in between. That's why it's called as binary convert to gray code. So how it look like? Basically, this is the equations that you can understand, but I think it's very more suitable and more understanding in the example part. Over here, I show you first. In here, you will get this one as the binary, and then this is the gray code. So every single this of binary, how you going to get your gray code? So you need to do this flow. First, you will get 1 plus 0, what you will get, which is 1, and then 0 plus 1, 0 plus 1, it will get 1, 1 plus 1, you get 0, and 1 plus 0, you get 1, and 0 plus 1, you get 1. So 1 plus 0, you get 1 over here. 0 plus 1, you get 1 here. And then 1 plus 0, you will get 2. But there is no just 2 in binary. So Later on you will check in the example part how it's going to move, and that's why if 1 plus 1 you will get 0 for the gray code, and then 1 plus 1 you will get as 1, and 1 plus 1 also you will get 1. So the gray code will generate. So maybe we can see it more clearly in the example. So move to example first. If let's say you were given the binary code of 100110, so this is the examples of the binary. You need to convert it, or what is the equivalence for the gray code value. So this is your binary, and you need to have the plus equation first of all, or the first example I forgot to make you bring this one, which is MBS will directly tag to the bottom, which is to the gray code. That's why you get 111011. Later on in the example you will see more clearly. So over here, how you will get, first you will get it and directly bring the MSB directly to below, which is this is the part for your gray code. And then I already show you that you need to add or plus. So over here, if you plus 1 plus 0, 1 plus 0, you will get 1 as the answer. Then 0 plus 0, you will also get a 0. And then 0 plus 1, you get 1. 1 plus 1, this is the situation when you get 1 plus 1, you will bring the answer as 0 because you will be doing the discharge carries. Just remember the scenario and what is basically the output, and you follow by 1 plus 0, you will get 1, and then 0 plus 1, you will also get 1, and lastly 1 plus 0, you also will get 1. So the answer of your gray code from this binary number is you get 1 1 0 1 0 1 1 1 for your gray code. Okay, now clear? Let's move to another example, but this one is you convert gray code to binary, but it's basically similar, only it's reverse situations or scenario, because you have the gray code on top and the binary code is on below or bottom. So let's say you have 11010111. So over here you will bring it directly to the binary code, because if let's say you have numbers over here, you also bring it directly to the gray code. And next is on, if let's say you have 1 over here, what you're going to do is you need to add if let's say you want to convert binary to gray code, you will add all the numbers in the binary itself, right? So you will add this and then you will get answer, you add this, you get answer for the gray code, you add here, you get the answer for your gray code, and etc. But now it's reverse way, which is gray code to the binary. So that's why you need to add binary numbers or value to the gray code that given from starting from the MVS that already given. So 1 plus 1, as similar as the scenario with the binary convert to gray, it will be the discharge carries, which is you will get the output of 0. And then 0 plus 0, you will get 0 as your binary number. And then 0 plus 1 is what? 1, because 0 plus 1 or 1 plus 0 is 1. Next is 0 plus 1, also 1, and then 1 plus 1, you get the discharge carries, and you get over here as a 0. Similar also here, 0 plus 1, you get 1, and 1 plus 1, you get 0 as a discharge carry scenario. So easy peasy, right? So what you're going to get for your binary from this gray code is you get 1 0 0 1 1 0 1 0 as your binary numbers. So please try to do this exercise. You need to convert this binary code, and you're going to get the gray code value. You get this binary. First you draw the table for your binary. You have 1 2 3 4 5 7. Okay, you have 0 0 1 0 1 0 1 1. You are unlucky to have this lecturer because she write very ugly in numberings. So over here, is it similar? 110 110. Okay, so this is your binary, and you need to get another table for your gray code. First of all, you will bring it the numbers, and you will add here 1 plus 1, you will get 0. 1 plus 0, you get 1, and you do the rest. What is the answer? Okay, it's quite simple on converting it. So now it's on the parity codes. How about parity code? Parity code, over here you need to calculate how many 1 or first digit numbers, whether it is even or odd. I don't want to show more in this slide because the next slide is much more important. Here on this table, you need to memorize this table. It's quite simple. You just draw a basic table which is even or odd in the ones. What is this? Later on I will show you. And then for even parity, if it is even for the first or one digit, you will get over here 0. And then if let's say it's odd, it will get also 0 over here, like this. I think so. Yes, okay. So you just remember this table, then you can directly convert it. So let's go for the example. You need to calculate first how many one digit are available in the given numbers. So 1 2 3 4 5. It is 5. 5 is ganjil, so it will be odd number. Okay, if you want to have the even parity for odd number, you will get even parity, so you will get 1. Where are you going to put this one? This one value, you will put it in front. Why? Because you have total of 1, 2, 3, 4, 5, 6, 7, 8. You put over there as the even parity. And then over here, how many ones? 1, 2, 3, 4, 5. 5 similar to here, it is odd number, and if you want the odd parity bits, under odd tables, odd parity, so you need to add 0 in front. I think this one is much more easier because we just need to have the simple tables. Next, I give you more examples. If let's say in the 7 bits of data, you want to have the add bits including the parity. So the parity that you're going to add, this is the bit of parity which similar to this one. This is the parity bits that you added depending on these tables. So over here you have 0, 0, 0, 0, 0, 0, 0. How many 1? How many digits 1 that available in this number? None, right? So that's why it is 0. 0 is ganjil or genap, or even or odd numbers. It is even numbers. So if it's even numbers, if you want to have the even parity, you will get as 0, and if you want it's odd, you're going to have 1. So you need to remember the tables, how it look like this. Okay, you have the even number, ganjil, sorry, and then you have odd, and then this one is how many digit 1 that available in the number given to you. And if you want the parity of odd, okay, let's say over here even, and then odd parity. So if you want the parity of even, you will get like this, 0, 0, and then odd will be like this. So just remember this table. This is for parity, what parity that you need to convert to. So you need to add the parity bits. How is it? If it is 0, 0, 0, 0, no bits which is uneven. So if you need to even, you need to add 0 to in front. To in front this number, you need to add 0. For odd numbers, for odd parity, you need to add 1 in front. So this is what you get as the parity bits. You will add as 1. And then over here, the second example, you have 1, 2, 3 digit 1, so it is odd numbers. So odd times of 1, which is odd numbers, you need to have the parities of even. You will add parity bit 1 in front. That's why you get here this one. And then for the odd, you will get 0 in front. So for third example, you will 1, 2, 3, 4. You have over here 4 of the bit 1, and that it is the even. So even you will get 0 as a parity bit. For even parity and odd will be get 1. Over here, the example number 4, you have 7. 1, 2, 3, 4, 5, 6, 7. 7 bits of 1. So you will get it as a odd numbers or odd numbers of 1. How many ones available? And you will look into these tables. If you want even parity, you need to add parity bits as 1 in front, and if you want to convert it into parity of odd, you will have the parity bits of 0. Simple, but after this you will use this in the ASCII code. So this table, not this one, I want you to do, this one is also you can try, but I want you to do, where is the table? Okay, later on this one. Before that, okay, let's take a look this example first. This is just simple, similar also. I can give you the examples, which is 1, 2, 3. This is the odd numbers. Odd numbers of 1 is odd, so you will get, please remember the tables. I don't want to draw, it's really ugly. So you just fill in everything inside, and you will get the even parity or maybe odd parity for each of coordinates given. And this one is you can just go through it, error detection by parity checking whether it is even parity or maybe you have a odd parity in that. And this is important with the ASCII code. That's why I want you to look into here. If let's say you have the ASCII code, it has 128 characters and symbols represented in a 7-bit binary code. Example is if you have A for your ASCII, you have this binary code. So normally in computer, let's say my name is Liza, and there is A in here, so the computer did not recognize A, but when you press A in your computer keyboard, at your computer keyboard, basically your computer is reading it as 100001. So these represent as A, so like examples, but this one is capital letter. If you type the small letter, the code is different, which is computer just know this one, which is 11000001. So it's different as long as computer can understand it, but we as a user, we just normally know, okay, this is A cap locks, this is B cap lock, and etc. But computer needs these codes as to do the process and program on what data input that were given. A parity bits is added so that total number will be at a byte. So over here altogether 1, 2, 3, 4, 5, 6, 7. You have only 7 bytes. 7 bits over here. So what you're going to do is you need to add parity bits. That's why you need to learn first on parity. So you need to add parity as to make it to be add bits, which is 1 byte. So let's move over here. This is the example tables of ASCII code using your hexadecimal and also your decimal, but this is more useful because this is a table for your binary 7-bit binary, and you convert it into ASCII code. How? This is the example. If you have this number, what is this basically? 100. This one, I am too lazy to convert to calculate right now, but how you going to get, you need to refer to this table, which is you will bring this one to over here. This is the part is 110, and then this one to be something, okay, over here. So let's draw and meet it up until here. So that's why you get basically M as the ASCII code. You have long numbers over here, 110, 1101, but basically you just know that it is M as the ASCII code. So maybe you can have basically find, let me try to find my name. So I need to have L. So let me put L first. L I Z E. Let me erase everything. Or I want to have my name L I Z A, and I have over here L. I want to use just all cap lock L, so I will have 100 because it's something over here, and this one is 1100, but it is 7 bits, if you can see. And then I have I, so I have 100 and 1001 over here, and Z. What is this? 101, and then it is 1010. Another one is A over here is 100 and 100, and then 0001. Is it? Okay. So this is my binary numbers for my name. So if you can see over here, this is my binary number. And if let's say you have the very secret message to your girlfriend or to your boyfriend,